Presentation will present similarity search in high dimensions via hashing. Um, so the main intuition here is that we have this set of points and we project these points on random lines. So this is line number 1, line number 2, line number 3. And after these points are, we divide this line into a buckets like this using these separators, and points that are projected to the same bucket are expected to be similar to each other. So this is the main intuition of local sensitive hashing, where we have these random lines. You can think of these lines as hash tables, and the projection is like the hashing function. So project these points into this hashing table and this hashing table and this hashing table. In this example, every line represents a hash table. So in this example, we have 3 hash tables. And every hash table is divided into like entries. So for example, this entry contains these 2 points, the blue and the gray one. Now that the intuition has been presented, I will go over the algorithm as illustrated in the paper. The paper makes 2 main assumptions. We assume that the points and the distance between points are measured using L1 NOR. It is argued in the paper that L1 is equivalent to L2 NOR and that L1 is equivalent to the Hamming distance. Like, more information about this assumption and their argument are available in the paper. The other assumption in this paper is that points has to be positive integers. Again, it is presented that if the points are negative, you can just shift them. If they are float, you can multiply them by a big integer. To illustrate LSH, I will give a concrete example. In this example, I have 4 2D points. Every point here is represented by 2 dimensions, x and y's. In order to apply LSH, we need to map these points into the Hamming space. The actual implementation, we will not need to do this Hamming space mapping, but this is just for illustration right now. So right now we have the dimension for the original points is 2. We have 2-dimensional points. We find the maximum coordinate in these points, which is 5. This is a maximum number in this coordinate set. So we the dimensionality of the Hamming space that we are going to map the points to will be d dash, which is equal to c, which is 5 times d, which is 2, so it's 10. And the conversion is actually very simple. So if we have 2, this becomes 2 1s followed by 3 zeros. 3 becomes 3 1s and then 2 zeros. 1 is 1 1 and 4 zeros, and so on. This is very simple. And as you can see, 5 will become 5 1s. And this should explain why the d dash has to be 10. It can't be less than 10. Once the points are mapped to the hashing space, we need to set the number of hash tables that we're going to use. In this example, I'm going to use 3 hash tables, which is equivalent to saying that I need 3 hashing functions, 1 for each table. In this example, I'm going to set the hashing table size to be 16 entry, which is 2 to the power of 4. These numbers are user defined. There is no particular rule to set these numbers. There are some heuristics, but for this examples, I'm going to use this relatively simple numbers. So right now, the number of hash tables is 3. L is equal to 3, and each hash table has 16 entry, which means that every entry is represented by 4 bits. Now, to define the hashing functions, we need 3 hashing functions, and we need a way to define this hashing function. The way presented in the paper is to randomly pick 4 numbers randomly with replacement from the set from 1 to d dash. Remember that d dash in our case was 10. So we need to pick 4 random numbers from the set between 1 and 10. So here are my 3 hashing functions: I1, I2, I3. These numbers are randomly sampled, so you can, if you want to do this on your own, you will probably sample different 4 numbers, but the basic idea is that we need to sample 4 numbers. Now that we have defined our hashing functions, we can map the 2D points into the hash tables. So the first hash function was 1, 2, 3, 4, which means that we need the bits at these locations. So the first, second, third, and fourth bit. So that's we have 1, 1, 0, 0. This means that the first point, 2 and 3, will be inserted in the first hash table at index 12. And then we go to the second hashing function, which is 3, 4, 8, 10. So we pick the bits at these locations. The third bit is 0, fourth bit is 0, the 8th bit is 1, and the 10th bit is 0. So 0, 0, 1, 0. This indicates that this point will be inserted in the second hash table at index 2, and so on for the third hashing function. I will do this for the last time here. So 3, 5, 6, and 10. So we need to pick the bits at index 3, 5, 6, and 10, which should give you 0, 0, 1, 0. This again indicates that this point 2 and 3 will be hashed in the third hash table at index 2. You can do the rest. The rest of the calculation is available here. I will not go over it right now, but there is one point that I need to express, that these random sampled integers are now sorted, and this is a computation trick that will be explained in the next slide. Remember that we don't want to actually map the points into the Hamming space. This will be computationally inefficient. So we need a computation trick to compute the hashing function without actually mapping the points to the Hamming distance. So how we are going to do this? Okay. For I equal 1 to d, remember d is equal to 2 in our example. We define I to the I to denote in sorted order. In sorted order, this is important. The coordinates in I which correspond to the ith coordinate of b. So this is our third hashing function, 10, 3, 5, 6. We are going to define I3 to 1 to correspond to the coordinates from I3 that correspond to the first coordinate of B. So that's 3 and 5. Remember, 3 and 5 refer to the third and fifth bit in the Hamming space. So we are going to take these two in sorted order, and this becomes I3 to 1. I3 to 2 will be 6 and 10. Why is that? Because 6 and 10 refers to the 6th and the 10th bit in the Hamming space, which refers to the second coordinate of B. So 6 and 10. I'm going to subtract 5. Remember, 5 is C, capital C, which is the maximum coordinate in our space. So I3 to 2 becomes 1 and 5. You will see that this whole trick, the sorting, the subtraction, will make the computation of the hashing function very efficient, and we will not need to map the points to the Hamming space. To understand this computation trick, it's important to observe that projecting I dash on I to the I results in a sequence of bits which is monotone, meaning that it consists of a number of ones followed by 0. The number of ones can be 0 ones followed by a set of zeros, but it has to be always 1 and then 0. There is no chance that the projection will become 0 followed by ones. So let's give an example to make this concrete. Remember, this is our third hashing function, original one. This is I3 to 1, 3 and 5, and this is I3 to 2, which will become 1 and 5. Now this is B in the original space, 2 and 3. It's a two-dimensional space. This is a mapping of B into B dash, which is 1 1 followed by zeros, and then 3 ones followed by 2 zeros. If you try to compute the projection of B dash on I3 to 1, you will find that it is 2 zeros. The third and the fifth bit, which is this bit and this bit, it will become 0 and 0. While the projection of B dash on I3 to 5 to 2, I3 to 2 is the first and fifth bit in the second coordinate, so it becomes 1 and 0. Notice that it is always a monotone sequence of bits. It should always consist of a number of ones followed by 0. Remember, we are suggesting this computational trick to avoid computing the Hamming space in the first place. We don't want to compute B dash. So how are we going to realize this? Let's go back to our example. So I3 to 1 is 3 and 5, I3 to 2 is 1 and 5, and let's say that we have a point 2 and 3. All we have to do, so yeah, 2 and 3 is like x equal 2 and y equal 3. To get the projection of B on I3 to 1, we need to find the index of 2 inside this set. So 2 is less than 3. So it is less than all the elements in this set. This means that the projection of B on I3 to 1 will be a number of zeros. It has to be zeros. The number of zeros is equal to the number of elements in this set, which is 2. We have 2 elements here, so it becomes 0 and 0. For the y coordinate, we try to find the index of 3 inside this set. The 3 goes inside here between 1 and 5. This means that we have 1 1 and 1 0. So that's why we have here 1 and 0. So the final projection of point 2 and 3 on the third hashing function will become 0 0 and 1 0. It is important to realize this. In order to find the index of 2 inside this set, which is sorted, this can be done in order of log d log c or order of d, depending on how we are going to represent this set. As you remember, this set is always sorted, so finding the index of an element in such sorted sets should be efficient, and thus the computation of the hashing function.